Good morning, ladies and gentlemen. Welcome back to Kaduna State Senior Secondary School's Online Connect, powered by Exponential Computers. Physics lesson for SS1 students. So we are at the second week or week 2 for the physics lesson of SS1 students. I, the presenter, Ismail Baraya. So for the second weeks, here are the contexts for physics class. The number one is the work done in a force field. The second one is the types of energy. And when we say type of energy, we specify the context specify here because it's talking about the mechanical one. So the mechanical one are the potential and the kinetic energy. So these ones are the main context for the types of energy that we are to talk about. So also the last one is the conservation of mechanical energy. So here are the contexts. Okay, and let's go and see. So work done in a force field, and normally when we say work done is equal to the F times the D, that is the force times the displacement, and the force that you use to complete that work, to the work to be done, that is the W is equal to F times the D, the distance or the displacement between them. So the work done when lifting a body, when you are about to lift a body or an object. So that is the work done that we are talking about in a force field. So if you are about to lift a load through a height, and the height is the height, so a falling force must be applied to overcome the weight of the body. And you see any body, it has a gravitational force existed or obsessed with it. So any particle or any mass, because when we say mass, we are talking about the quantity, and any mass that have, or any particle or any object, that the gravitational force or the gravitational field exists on it. So if you are about to lift it off, and that up has to be straight offward, and that object, for you to carry it, you have to use your energy. You have to use your energy for you to be able to complete that work, for that work to be done. So therefore, when an object is lifted vertically upward, the work done is the work is done against the force of gravity or against the weight of the body. And so you see, when the work is done, and if you do that kind of work, it means you go against the force of gravity. And when we say you go against the force of gravity, normally the gravity is coming downward to the earth. Any object, when it go up, the earth's gravitational force has to absorb it. It will absorb it down. It will force that object or that particle to come down. So if you are about to carry something upward, that means that you go against the force of gravity, the force of the gravitational force. So for you to do that kind of work, you have to go against the force of gravity. And if you do that kind of work, and that work to be done, that is, you do the work in a force field. That is when lifting a object or a particle. If you look at this diagram, it is about lifting an object up to some height, and that height is the h, and the w, the weight of that body, or of that particle, or of that object. And if you go upward vertically, and when we say vertically, you know what we mean. So if you go upward with it, that means that you go against the force of gravity. That means you go against the gravitational force of the earth. So normally anything you throw it offward, then that the gravitational force will absorb it, will push it, will absorb it downward. It will come down to the center of the earth due to the gravity. That is the gravity, or due to the gravitational force. that exist on the earth, on the planet. So that is when lifting a body, you have to go against the force of gravity. And if you look at this diagram is trying to show a work done in a force field, but in a force field is about lifting an object, and that force you have to go against the force of gravity. You are trying to go upward, so the gravity is trying to push you downward, and you use your energy, you apply your force, you put your force to it, and you complete that work. That is why the work is done when lifting a body or a particle. Okay, so the second example here is a work done when pulling bodies. So you see this one, if you understand the second one is talking about against the force of gravity. So this second one is not against the force of gravity, because it is also going to the direction of the force of the gravity. So when a body falls in a force field, the force of the field does work on the body. Hence, for a body falling freely under gravity, the Earth's gravitational force does work on it. So if you look at this statement, this statement, the Earth's gravitational force does work on it. So you see, normally when an object or a particle is falling down, that means that it's not going against the force of gravity. It's coming down freely by itself. Maybe an apple. If you look at this example, it is an apple falling down freely. It is not going against the force of gravity. It's not trying to interact with the force of the gravity. They are going the same with the direction, because it is falling down. It is a downward. So it's not going against the force of gravity. So when it is freely coming down, then the gravitational force on the earth will absorb it, will push it downward to the center of the earth. That is why it says the gravitational force does work on the body. So you see, when a body fall in a force field, the force of the field does work on the body. So it work on the body, it absorb, it push that object or that particle or this apple to come down due to the force of the gravity, due to the gravitational force that exists on the earth, on that particle. So it will come down, because it is not going against the force of the gravity or the gravitational force. So it is a work done when falling bodies, when they are falling freely. So it is not going against the gravitational force, not going against the force of gravity. They are going in the same direction. So this is about work done when falling bodies. So when a body is lifted or fall, so it does mean that whether it is going against the force of gravity or is not going against the force of gravity, the magnitude of the work done, that is the work done, is equal to the force times the distance. So this formula is used to calculate a body, whether it is lifted upward or it is falling downward. So this is the magnitude of the magnitude of the work done, and that says the work is equal to force times the distance. And this force, normally when we say force, we are talking about the mg, and this mg is the mass with the product of the gravity, that is the g, that is the gravitational, that is the acceleration due to gravity, that is the small g. So it's talking about the small g, that is the mg, that is the mass times the acceleration due to gravity. Then the distance between them, that is the height of the object, whether you are trying to lift it off, or that object or that particle is coming down. That is the distance, the displacement between them, that is height. And when we're talking about the distance, we are talking about the height. So the work is equal to mass times the acceleration due to gravity times the height, where the mass is the mass of the body, the quantity of the body, and the h is the height, while g is the acceleration due to gravity, which has a constant value of either 9.8 meter per second square, or 10 only, because if it is just 9.8, you can do the approximation. That is why we are having a 10 meter per second, and these ones, they are the constant value for acceleration due to gravity. They are not changing, but the mass of the body, it can change. It can be heavier, or it can be smaller. It is not heavier, it's not too heavy. And the height, it can be long and it can be short. So this one, they can change, but the acceleration due to gravity constant value is not changing. So this is the formula for calculating the work done when lifting an object or a particle, or when the particle, it is falling down. So this is the formula for them. Okay, so let's look at this example here. This example here says a body of mass. You see, we have our mass, and that mass is 50 kilogram, runs up a step of total height, that is 3.0 m, and this 3.0 m is the height of the steps. The total step is 3.0, that making it is 3 m, and we are to find the work done against gravity. So you see, we are to find the work done here. So if we know our formula for finding the work done, that means that, okay, before that, this question, we have to know that, is it going against the force of gravity or falling against the force of gravity. So you see, it is going against the force of gravity, because it is the boy is running off in a running up a step steps. He is running, going upward. So you see, it is going against the force of gravity. So the formula for work done is W O, work done, is equal to mgh, that is mass multiplication of the g, that is the acceleration due to gravity, multiplication of the height. So this one is the formula for the work done. So, and here we will just put our values, and that is the m has a value of 50 kilogram, that is, it is here, and multiplication times 10. So if you look at this, our question, we don't have this m. So you see, this m, if you don't know it, you will just wonder, where do we find this n, where did it come from? So it is a constant value. I told you before, this g, it is acceleration due to gravity. It is not changing. It has a constant value. It is not changing. That is 10 meter per second. So you see, and the times the height, that is 3. So if we multiply them, we multiply the 50 times the 10 times the 3, we will end up with 150 joules. And normally, work done, it is measured in joules. So you see, we find out the work done, the work that he done, in order for him to go against the force of gravity, we end up with 150 joule. That is the work done that we find for the boy running off running up steps. So you see, he is going against the force of gravity, and the work done that he do is, so it is 150 joule. So this is an example for the work done against gravity. Okay, so we are at the types of mechanical energy. So you see, the content already specify which types of the energies that we are about to talk about. It is specified with the mechanical energy. So it is these two. When we are talking about the mechanical energy, we are talking about these two types. So normally, the one that we have is the potential energy and the kinetic energy. So these two energies, they are the one talking about the mechanical energy. So mechanical energy normally is classified into two: the potential energy and the kinetic energy. And the abbreviation of the potential energy, that is P dot E, and this E stands for the energy, and the K dot E also, that is the kinetic energy. So this one are the types of the mechanical energies that we have. So let's go and see to the mechanical and the kinetic. Okay, so the potential. So the potential energy, we also know that it is the energy. So potential energy is the energy held by an object that has yet to be released. So you see, it is a energy that is held, and that energy or that particle, it is not yet to be released, and it is not released. So any kind of particle or any kind of object that whether you lift it up or it is at the top, it did not come down to the ground, that that object is it has a potential energy, because it is not yet released. If you have released it, then it is no longer potential energy. But if you lift an object off, or that object at the top, near top of a, maybe near top of a tree, that, or even a fruit on a tree, it is in the tree, it did not come down, so it has a potential energy because it is not yet released, or it did not come down. So potential energy is energy held by an object that has yet to be released. It is obtained, refers to as stored energy. So you see, it is a energy store, and when we say store, we are talking about something that is kept. It does mean that it is not moving. So it is the energy. It is also called a stored energy. So which has a formula of, and this is our abbreviation for the potential energy, that is P dot E, and is equal to mgh. So normally this M is stand for the mass, also for the G is the acceleration due to gravity, and also the H is the height. So and this potential energy, since it is energy, that means that it has to be measured in joule. So it has to be measured in joule, not in or newton or something like that, because it is energy. That means that it has to be measured in joule. And if you look at this diagram here, this small picture here, you will see that it is like an object or a ball. Let's say a ball that he lift it up, but he did not release it yet for it to come down. It is storing in his hand. That is why it is also called a stored energy. The energy is not yet released. If you release it to come down, then it's no longer, a potential energy. It is, we will talk about it. It is the kinetic energy will go there. It is no longer a potential energy. So anything that you lift it up, or it is at the top, but that particle, it contains a potential energy because it is stored, and it is measured in joules. So here is the example of potential energy. And firstly, we are to find the potential energy of a boy mass of 10 kilogram standing on a building. So you see, this one is talking about a boy standing on a building floor of 10 meters above the ground level. So you see, this we are to find the potential energy here, and the mass is given, and the height is given. So you see, and it is the mass of the boy, that we have the mass of the boy and the height of it, and we are to find the potential energy of that boy. So you see, and if we are to find the potential energy, then we already know the formula for finding potential energy, which says P dot E is equal to mgh, and we already know what is M, and the M also is given, that is 10 kilogram, and also the height, it is also given, that is 10. So we see we have our 10 here, 10 times 10 times 10. Okay, but if you look at our question again, if you can go back to our question, you will see that how many tens do we have? We will only have 2 tens. The 10 kilogram of the mass of the ball, and the height of also 10. That means that this constant value, you see, I told you it is a constant, it is not changing. It is either 10 meter per second or 9.8 meter per second square. So if you can use 9.8 meter per second, also is also the same, or if you can use 10 meter per second square is also the same, because they are the constant value for the acceleration due to gravity. So you see, if we are to just multiply them here, then we will find out the potential energy of that boy. Okay, and if we press our calculator, we will do the multiplication of 10 times 10 times 10. We will end up with 1000 joules. So this 1000 joules is the potential energy of that boy. So you see, if we are to find the potential energy, we have to use this formula for finding potential energy, so that we may be able to find the potential energy of a particle or of a body or of an object. So you see, this is the potential energy of that boy, that is the 1000 joules. So this is for the potential energy. So the kinetic energy. So the kinetic energy also is an energy, right? Yes, because they are the types of the mechanical energy. So this kinetic energy is the energy of motion. Okay, so that has to recall us back, because we have to think again when we say motion. What do you mean by motion? Then we are talking about the change of place. That is the movement. That is the movement. When we are talking about motion, we are talking about a movement of an particle from one place to another, from a distance, not in one place. So this one is talking about the energy that is in motion, and when we say in motion, we are talking about the energy is moving. So you see, and the one that we just finished, the example of a boy or holding a ball or something like that. If at the top of a building, if you that energy that you are holding for the potential energy of that particle, of that or of that body that you are holding, if you release it and it come down, so that means that that energy is potential. Why? Because it is in motion, because it is an energy of motion, because it is moving. So it is kinetic energy. Whenever the energy is in motion, is talking about the kinetic energy. So all moving objects have kinetic energy. So it's already cleared here, because it says all moving objects have kinetic energy, and kinetic energy is directly proportional to the mass of the object and to the square of its velocity. So you see, this is the formula for finding the kinetic energy, that says k dot e, that is the abbreviation, which says is equal to 1 division of 2 mv square. So this mv normally we know is stand for the mass, and this b is stand for the velocity, the square of the velocity, because it is a motion, it is in speed. So you see, when we are talking about the velocity, we are talking about the motion, right? Yes, the movement. So also this one also, it is measured in joule, because it is an energy. So it is also it is also measured in joules. So kinetic energy, if you look at that, any all moving object or any particle moving, that is moving, that means that it is a kinetic energy, it has a kinetic energy on it. So also this formula is for finding kinetic energy, that says k dot e is equal to 1 all over 2 meter per second square. So this m is the mass and the b is the velocity. So if you are to find the kinetic energy, this is the formula for finding kinetic energy. And also example of kinetic energy is like a student running a race. So you see, he is running. We are not saying he is standing or he is looking at a race. No, he is running. He is running a race. So you see, or an object falling freely under gravity, or if that object you leave you leave it freely, then it will fall. And the earth's gravity will absorb that particle to come downward. It will push it to come downward. So you see, it's also an example of kinetic energy, or a charged particle in an electric field. So you see, also those charges, the one that they are moving in an electric field. So you see, they are also an example of kinetic energy, and also it is measured in joule. So this is about kinetic energy. So here is the example of kinetic energy. An object of 5 kilogram, that is the mass, is moving at a constant velocity of 15 meter per second. Calculate its kinetic energy. So you see, we have our own mass here and we have our own velocity here, but the question says we have to find the kinetic energy. So you see, if you know our formula for finding kinetic energy, we may be able to solve this problem. So you see, the kinetic energy, that is Ke, is equal to 1 all over 2 meter per second square. So if you look at it, what is our mass? Our mass is 5 kilogram, and what is our B? Our B is the velocity, that is 15 meter per second. Okay, then let's put it into action. 1 all over 2, on all over 2 is here because it is from the formula. Then multiplication of 5 times 15. Okay, this 15, but it is in square, that means that we have to solve it. Then the second step, it says 1 all over 2 times 5 times, when we say 15 times 15, we will end up with 122, we will end up with 225. So this is for the multiplication of the velocity because it is in square. Okay, the third step is, it says also 1 all over 2 times, then we just multiply this 5 times 225, then we end up with 1100 and 1000. We end up with 1000, sorry, we end up with 1 divided by 2 multiplication 1000, sorry, we end up with 1125. That is our own value. So sorry for the error, sorry for it, please. Okay, and if we then with this 1125, we will just divide it with 1 all over 2, that is 0.5. When 1 divided by 2, we will end up with 0.5. Then multiplication of this 1125, then we will end up with 562.5. that is our due, 562.5. This is the value that we end up with the kinetic energy of that moving at a constant velocity of 5 meter per second, and the mass of the object is 5 kilogram. So this is the kinetic energy. So we are at the law of conservation of energy. So this one is a law. So the law says the principle of the conservation of mechanical energy states that the total mechanical energy in a system, like the sum of the potential energy, we are talking about the potential energy here, plus kinetic energy. So you see, the potential energy, when we are talking about the potential energy, we are talking about the energy that is stored, because we also call it a stored energy, plus the kinetic energy. So you see, and when we are talking about the kinetic energy, we are talking about the kinetic energy in motion, because it is moving. That is why it is a kinetic energy, remain constant, although energy may be changed from one form to another. So you see, the potential energy and the kinetic energy, they are in constant. So this law is talking about the constantity of the potential energy and the kinetic energy also, but the energy, it may be changed from one form to another, because it can change from mechanical energy to electrical energy, or from heat energy to electrical energy. The energy, it can change, but the potential and the kinetic, they remain constant. And when we say constant, we are talking about something that is not changing. It will not change because they are in constant. That is the law. This is the law of conservation of energy, that says the principle of the conservation of mechanical energy states that the total mechanical energy in a system, like the sum of the potential plus kinetic energy. So you see, the storage energy and the energy in the motion, remains constant. You see, they remain constant. These two energies, they remain constant, but the energy, it can change from one form to another. It can change into many kind of form, because the energy is used to come into many forms, because it may come into electrical energy or mechanical energy or thermal energy or heat energy or sound energy. So it can change into many forms of the energy. So this is the law. But this one, the potential and the kinetic energy, they remain constant. And when we say they remain constant, we are talking about they are not changing. So this is the law of conservation of energy. Okay, so here is let's all look at, let's consider this thing. Okay, then consider, this is the example for us to understand the conservation of the mechanical energy. Consider a gravity. You throw a ball. So when you throw a ball straight up, so you see the ball is straight up and it leaves your hand. So you see, before you throw it, that means that the energy is potential, because it is stored in your hand. You do not release it. So, and it leaves your hand with a certain amount of kinetic energy. So when it start moving, that means that it has it start with the kinetic energy, that is in motion, that is in moving. At the top of its path, it has no kinetic energy, but it has a potential energy equal to the kinetic energy. So you see, the potential energy has to be equal with the kinetic energy. Okay, when it leave your hand, when you catch it again, so you see, you catch it again, before it is potential, it is in your hand, then you throw it, and you throw it straight off. So, and also when you catch it again also, that means that it come back on your hand, it will have the same kinetic energy. That you see, the kinetic energy that it have before it is moving, before it's throwing it, will be the same with the kinetic energy that is returned on your hand. So all along the path, the sum of the kinetic energy and the potential energy is constant. You see, they will not change, because just like maybe if you are throwing a ball on the wall, so you will throw it, you will throw it also, you will catch it, you will throw it, you will catch it, you will throw it, you will catch it. That means that they will not change. The potential energy and the kinetic energy, they will not change, they are constant. So the potential energy is constant, and the kinetic energy at the end, when the ball is back at its starting point, is the same as the kinetic energy at the start. So you see, the kinetic energy and the potential energy will remain constant, just like this law, the one that we just finished explaining. They remain constant. The potential energy, that is the storage energy, and the kinetic energy, that is the energy in motion, they remain constant. Also, the energy, it may change into many forms of energy. So thank you for listening. I think this is the end of the today's class. This is the end of today's lesson. So thank you for listening. I wish you best of luck.